Hello, everyone. Welcome to another episode of Cuda Education. Today, I want to discuss the new files that were added to our application in order for us to create our triangle. So this was the triangle that was created. And in order to create this triangle, we had to add some new files. Now, in the previous episode, the one directly behind this one, we had some files that were modified, but we're not dealing with the modified files now. We're dealing with some added files that were used to generate the triangle. Okay, so we're going to discuss these files and figure out what's going on with them on briefly, a little bit more detail than maybe I'd mentioned before. But yeah, let us just get through it because I'm eager to keep the ball rolling. So in this particular episode, we had in this particular situation, we had three files that were added. We had APL simple.metal, and then APL renderer.h, which is the header file, and .mm, which is like the main file, right? So thing to note is that the .metal stuff is usually GPU related stuff, and the header and main stuff is usually CPU. But for the headers can be included in CPU side code and GPU side code. So the .mm is the main stuff. I have a whole episode that discusses the file types that we're dealing with, so I'm not going to rehash the whole conversation here. But yeah, so we have sort of a shader GPU side file, and then we have some CPU side stuff, and we're just gonna go through what exactly happened here. So let's just go to the metal file and notice that the .metal has this M icon here. I think you guys can see it in the window, right? So the .metal file, we have two metal shader functions, vertex simple shader and fragment simple shader. So vertex simple shader takes a view projection matrix and position buffer, transform each vertex to clip space, right? So when it says transform each vertex, this is a vertex, this is a vertex, and this is a vertex up here, right? So we have three vertexes. So it takes a view projection matrix and position buffer, transform each vertex to clip space, right? So that is the vertex simple shader. Now, here is vertex simple shader right here. All of this guy right here. Now notice that we have for vertex simple shader, we have a bunch of parameters, which we're not gonna belabor at this point, but just know we have a WVP matrix, which I guess is the view projection matrix, right? So that's the first parameter right here, this guy right here, and then we have a position parameter, which is this guy right here, right? So we have a position parameter, right? So takes a view projection matrix and position buffer, transforms each vertex to clip space. Okay, so basically it's taking some information, and then there's an extra parameter here, but vector ID, right? So I guess for the three vectors, and then it's outputting the proper position and transforms each vertex to clip space. So it's outputting a new position based on clip space and all of that. Don't really want to dive too deep into it at this point, but just understand that this vertex simple shader, it takes in some parameters and then it outputs some new information that's adjusted for clip space. All right, and we'll leave that alone for now. But I do want to mention is that we need to pay special attention to the name of this function, vertex simple shader. It's going to come up when we get to the AAPL renderer files, right? So we have vertex simple shader, and it's this function here, right? And just remember this name because it's going to come up again and it's going to be kind of important. Okay. All right, so now we have our fragment simple shader. Takes a color and outputs it directly. So we have our fragment simple shader here, and we have a particular color that it accepts, which is this guy right here. And then we just return that color to the screen. And this is what is responsible for the orange color that we see here. All right, so we have an orange colored weird triangle, but triangle nonetheless. Okay, and that's all the fragment simple shader does. Now APL simple vertex out, it's just a position, a strut with a position thing in it. Just you know, observe, and we'll leave that there. Okay. So let us just again look at abstract simple vertex and fragment shaders for basic geometry rendering, right? So when we import simple shader type, we include metal standard library and SIMD. So yeah, so that is the APL simple dot metal in its entirety. Okay, so then now we get to APL renderer. So what is this? The renderer class now owns the entire metal pipeline. So we have init with metal kit view, sets up the command queue, compiles shaders with a pipeline state, creates a depth stencil state, creates a vertex buffer with 3 triangle positions, creates a color buffer orange, and initializes the camera. Okay, so we have previously discussed that the things have been moved away from the view controller, which is just a UI interface kind of storyboard thing, and we put the heavy lifting for rendering and the logic for drawing to the screen and everything in the renderer files and the renderer ecosystem. Okay, so that's going along with that. This is just simply a header file, so this is just like an include file. So header for the renderer class, which performs metal setup and per frame rendering. So we import metalkit.h, interface APL renderer. We have our MTK view delegate here, and we have init with metal kit view and all of this stuff here, right? So the init with metal kit view sets up the command queue, compiles shaders into a pipeline state, creates a depth stencil state, creates a vertex buffer with 3 triangle positions, creates a color buffer orange, and initializes the camera. All right, so we get to let's get to the main file now. So that's this guy, and we'll start from the top. Implementation of the renderer class, which performs metal setup and per frame rendering. So we include our header file, we import the header file. We also import APL camera, and we import APL shader types, right? So using namespace SIMD, and then yeah, we have a bunch of stuff that's going on here. Let us see what actually it says for the drawing MTK view. Per frame, updates the camera, encodes a single triangle draw with the view projection matrix, presents and commits. MTK view drawable size will change, updates the camera aspect ratio on resize. So this update the camera aspect ratio on resize is when you change. So right now I have a full screen window. If I change it to a smaller window, or if I adjust the dimensions of the window, the dimensions of the pixels and everything and what is drawn will adjust accordingly. Okay, so that's that guy here. But so notice that we have our variables. We have all of our variables here, right? APL renderer. We have our device, command queue, simple pipeline state, depth stencil state. We have our vertex buffer, color buffer, and our APL camera, which is just this camera variable here. Notice that we imported the camera, we imported the renderer stuff, and we have our shader types and everything. Init with metal kit view. So we have, we do all our device, the command queue, all of that stuff is now inside of the renderer files. Configure the view. We have color pixel format, depth stencil pixel format, clear color, load shaders and create the shader pipeline state. Load shaders and create the render pipeline state. So we load metal with view, create triangle geometry, load assets, create camera. We have our camera here, and then we have our aspect ratio calculation, which is the width divided by the height, and then return self. So this is all within the init with metal kit view function. Load metal with view. So load shader functions from the default library. So we have MTL library, default library, new default library. We have our vertex function. So remember I said we needed to make sure we paid attention to the name. The vertex function is going to be at vertex simple shader, right? And which is coming from APL simple.metal. And then we have our fragment shader at fragment simple shader, right? So this is what is attaching to. We're setting up the pipeline. We're setting up things properly. So we're attaching the vertex function and the fragment function to our shaders that we built in APL simple.metal. Okay, and then we create the pipeline, the render pipeline state. So we have MTL render pipeline descriptor, and we attach everything. Now we're really attaching stuff. So we have our simple pipeline state here, which I guess is this guy right here. Yeah, maybe that's in. Okay, so we have our simple pipeline state. Oh, maybe that's just the label for this thing. No, that's just the label for this thing probably, right? So we have a label for this pipeline. We have a vertex function. We have a fragment function. We have a color attach format. View.color attach format. Which I guess would be this guy right here. Color pixel format, right? Right, color pixel format, okay. So color attach pipeline description, color attach pixel format is view.color pixel format. And we have our depth attachment pixel format, depth stencil format, right? So we have this guy right here. I'm gonna say this is error checking. So simple pipeline state equals device new render pipeline state with descriptor pipeline the descriptor, right? So this guy right here, right, which is all of this right here, right? So new render pipeline state with descriptor error this guy, right? NS asserts simple pipeline state failed to create simple pipeline state, right? And then the error. So this is error checking to make sure that we actually were able to create the pipeline, which is you're basically collapsing, you're cascading, you're compressing everything into this variable, and then you run it and you try and create the pipeline. And if it fails, it tells you, hey guys, we failed to create the pipeline. But if not, then we continue. Create the depth stencil state. Okay, so we create the depth stencil state, and this is not necessary. We don't really need this stuff, and it's not really necessary for what we immediately need to do right now, but it is for once we start developing the application and moving on to bigger and greater things. So because of that, we're not, we have to sort of lay the foundation even though we're not using it fully right now. So anyway, we have this depth stencil state thing, which I think this is what's used for depth testing and seeing if one object occludes another, which basically means is the current object we're rendering blocking a previously rendered object, or is the current object that we're rendering makes it unnecessary for us to render stuff behind it because it's going to be occluded, it's going to be blocked, all of that stuff, right? But that's a topic for a different day. We need to do the depth stencil stuff, so here you go with the depth stencil stuff. The compare function, MTL compare function less. In my previous metal videos, I actually played around with the depth testing, and this function came up. So metal MTL compare function less. Certainly, you guys could research this function yourself, or just go back to the videos that I had previously on Apple Metal, and you will see this in action. Depth right enabled, yes. Depth stencil state is device. New depth stencil state with descriptor, depth descriptor. Okay, so we now have our depth stencil state variable here. That variable was initialized up here, right? So we have our depth stencil state function up there. Okay, so now we're loading assets. Hard-coded triangle vertices low placed in front of the default camera. Blah blah blah, looking towards this, that, and the third. Okay, so we have our vertices here. Bottom left, top right, bottom right. Vertex buffer. New buffer with bytes. We have our buffer. We have remember our buffer is like a bucket of memory, right? So we have to have, for the vertex buffer, we have to have a space in memory to save all this stuff, right? So we have triangle vertices, which is this guy. We have, what is the length of the triangle vertices? Well, it's 3 vertices. And then MTL resource storage mode shared. So, we're trying to say what is the mode that we're sharing it in. Same thing for color. Size of color is the length. New buffer with bytes, color, and MTL resource storage mode shared, right? And then we go through drawable size will change. So remember, camera aspect ratio is width divided by height. MTK, draw an MTK view. Remember, per frame updates the camera, encodes a single triangle draw with a view projection matrix, presents and commits. Okay, so this is now, I think, where we're going to get into encoding and all that stuff too, right? So update camera matrices. So camera update state. Yeah. We're actually going to get into, I'm going to do another episode where I go into detail with all of these new files. So don't hesitate if I'm glossing over stuff now. Literally in the next episode, I'm gonna go into detail with these lines of code, and we're gonna rock with the agent and figure out exactly what's going on here. So don't despair if I'm glossing over some stuff. Right, so we have our view projection matrix, which is this guy right here. Get the render pass descriptor. View.current render pass descriptor. Okay. This guy we will have to. That's that view variable. I guess that's all of this right here. Right, so init with metal kit view, and then we have our view thing right here. So that's what that is right there. Okay. Get the render pass descriptor. So we do view.current render pass descriptor. Okay. And then if it doesn't pass, we return. Okay. Create command buffer and render encoder. So we create our command buffer, and then we have our render encoder, right? So I guess the encoding starts here. Set pipeline state and depth stencil state. So set render pipeline state, simple pipeline state, set depth stencil state, depth stencil state. Okay. Set vertex buffer positions. Set vertex buffer, that's our vertex buffer, which we saw previously. Offset 0 at index APL buffer index vertex mesh positions. Okay. Set camera view projection matrix. Blah blah blah. Set fragment color. Right. So we set the fragment color. Draw the triangle. And we draw a triangle and we end encoding. And then of course we got to present drawable to the screen and then we commit our command buffer. So all of this stuff is instructions that we're giving the GPU to do stuff, right? And that is exactly what gives us our triangle here. Now, this kind of concludes our discussion of the 3 files that were added to our project. Again, in the next clean slate 1.6, I guess I will call that. I don't even want to do that because I might end up doing something different. But the next video that's going to discuss this in detail is probably, you know what, it's probably going to be clean slate 1.621. Okay, so that next video is going to be a child of this video. In software, guys, we have version numbers, and I'm just trying to adhere to the logic of the version numbers, the version numbers, so that you guys can follow. So I'll go into more detail with this stuff. But what I do want to do, is I want to play around with the vertex count, okay? So remember, this is the encoder now, which is actually, we're encoding stuff and we're actually handing it off to the GPU because we're committing the command buffer and stuff. But what we're going to do is I'm going to mess around with the draw triangle. So instead of it being 3 vertices, I'm going to do 2 vertices. And we're going to just replace, and we should get our we should get nothing, which is odd. So if I do 4, replace. Okay, so if I do 4, I get, so if I do 1, before I used to get, let's stop it. Oh no, it wasn't the vertex count. Okay, I get what's happening. It wasn't the vertex count that I changed. What I changed is the vertex start. Right. So I don't start at 0, I start at 1. So when I start at 1, as you can see, we only get like 2 vertices or whatever instead of the 3. Now if I go back to 0, I'm gonna get my, so let's do 2. So if I do 2, all right, well, you guys get the picture, right? And if I do 3, I'm not gonna get anything. Yeah, all right, but you guys get the picture. Let's put it back to 0, and then we should get back our normal triangle. All right, so you guys get the picture. All right. So what I also wanted to do was so this was the draw primitive, but I think I could also tinker with the vertex buffer itself. Yeah, basically it's a crash. But let's not mess around with that. All right. There was something else I used to mess around with, but I can't remember right now. It was something to do with the at index. But anyway, let's not get carried away. Let me make sure I still have my regular triangle. Still have my regular triangle. All right. Yeah. All right, guys. That's it for this video. You guys get the picture. So we are a little bit more comfortable with what's going on here. Um, we're getting closer and closer to actually seeing our bistro. So that's really what I'm excited about and what I want to get to. But right now we're just still at triangles. We gotta just get through certain things and do things in a proper way so that we're in a better position to understand what's going on when things get really fancy and you know appealing and stuff. So this is Cuda Education, guys. You know what to do to support the channel. Tell your friends, build your community. um, get your friends together to learn this stuff. We are programming the GPU, which is probably the most important piece of hardware in modern times. So, um, let's get to it. Thank you for watching. Have a great day.